Let's discuss a type of integral that many calculus students don't see until Calc 2, and that's an improper integral. So here we have the integral from 0 to 1/2 of dx over x times this quantity natural log of x to some power p. And what we're going to go ahead and talk about is 1, why is this an improper integral? And 2, what is the value of p that is going to give us an actual solution to this integral? So the very first thing that we should mention is, why is this considered an improper integral? Well, if you look at the bounds, we are going from 0 to 1/2. Always look at the upper and lower bounds. So when you plug in 0 into here, you're gonna get 0, that's one thing, and then you get natural log of 0, and that's another thing. That does not exist. In other words, this function is undefined at 0. The other value that it's gonna be undefined at is gonna be 1, because natural log of 1 is equal to 0. This also makes it undefined, but we don't really care about that because it's only from 0 to 1/2. So the reason why it's an improper integral is because it's not defined at 0. So what we have to do, unfortunately, is create a limit. So we're gonna go ahead and do limit as b approaches 0 from the right side. And the reason why we're doing it from the right side is because if you look at it from here, you're going from 0 to 1/2. We're trying to approach 0 from the right side. There's no way that we're going from the left because we're starting at 0 and going to 1/2. So that's just a formality that we like to write whenever we're dealing with improper integrals. And now we can go ahead and do the integral from b to 1/2 of 1 over x natural log of x to some power p, and this is going to be to with respect to x. Okay, so I kind of moved the dx on the outside. So now what we're going to go ahead and do is we're going to go ahead and start solving this. Whoops, there should be a p right here. Before anyone screams at me, I'm just going to go ahead and change that. Okay, we're going to go ahead and solve this using u substitution. So we're going to make our u value natural log of x. So we have u is equal to the natural log of x. We're going to find du is equal to 1 over x dx. By the way, do you notice that these colors are a little different from all the other blue colors that I've had? For example, this is a different, it's the same brand, but just, I don't know, different company. Look at that. It's a little brighter than this one. I don't know. Let me know which one you like. But anyway, let's go ahead and multiply the x to the other side. We have x du is equal to our dx, and this right here is going to be our differential that we're going to go ahead and plug in here. Now, before we plug in our values, we need to change our parameters. So when x is approaching b, we're going to go ahead and plug in b in here. So when x is approaching b, we're going to have that u is equal to the natural log of b. Okay, not bad. And then when x is equal to 1/2, which is the upper parameter, u is going to equal to the natural log of 1/2. Now we can change that to negative natural log of 2. We're not going to do that. We're just going to leave it like that. Okay, let's go ahead and start rewriting our integral now. So we have the limit as b approaches 0 from the right side. Always got to write that. And then we have the integral from natural log of b to natural log of 1/2. And now what we have is 1 over x u to the power of p times x du, which is our differential. We did this so the x's can cancel out, and now we can go ahead and rewrite this as the limit as b approaches 0 from the right side. And then we have integral of natural log of b to natural log of 1/2. And I'm just going to go ahead and rewrite this as u to the negative p with respect to u. I did that because obviously we have to implement the power rule. Let's go ahead and implement the power rule by adding 1 to the power divided by the new power. So what do we have? We have the limit as b approaches 0 from the right side of u to the negative p plus 1 over negative p plus 1, all evaluated at natural log of b and then natural log of 1/2. So we're going to implement the first fundamental theorem of calculus. Let's go ahead and plug in natural log of 1/2. We have the limit as b approaches 0 from the right side of, we have natural log of 1/2 to the power of negative p plus 1 all over negative p plus 1 minus, and then natural log of b to the power of negative p plus 1 all over negative p plus 1. And there we go. We just need to find this limit. So remember, we just need to figure out the value of p that's going to help us give us this value. In other words, we want this to converge. Well, if you notice, the first value over here doesn't have a b whatsoever. So whatever the value of p is going to be, we're always going to have some value, whether it's going to be some crazy natural log of 1/2 to the power of like 1/2 to the power of 1/4. It doesn't matter. We always get something here. So we're not really worried about that. What we're worried about here is we are worried about this particular value, because when you are technically approaching b or 0 from the right side, this will become negative infinity, and we don't want negative infinity on the top. Because if we have infinity on the top, we have infinity over some value, that's just going to approach infinity. What we want though, is we want infinity to be on the bottom, because when you have a value over infinity, well, that's just 0, and that's really nice. So this limit will cancel out. Well, how do we get infinity to be on the bottom? we make this value, the power, negative, because if you have a negative power, it's gonna go down below. So what we want ultimately is we want this value, negative p plus 1, to be less than 0. We want it to be negative. So if we move the 1 to the other side, we have negative p is less than 1, or negative 1, and then we divide by negative 1. P has to be greater than 1. This is the solution of p, or the value of p, that's going to give us a value. We don't know what that value is, but we just know that p has to be greater than 1. As you can see, improper integrals can be fun, but this is one of those conditions or types of problems that you see in calculus too. In fact, this is sort of like the idea of p-series, where if p is greater than 1, then this limit or this integral is going to converge. Otherwise, it's going to diverge and it's not going to have a solution.